Thank you very much. Probably a very kind introduction. And also I have had very, very fruitful time. Many persons are very, very kind, and also the scientific level is very high. So today's talk is the third lecture. So the third lecture is, I think, this one is for the, I prepared this one for the undergraduate students, graduate students. But today's audience is professional. So this is a little bit, I'm afraid about that because this lecture is very basic. But it's okay, so I can do that. Okay? So today's lecture is new methods for organic synthesis using organometallic compound. I know many professors is expert in this area. So please be patient. Really long time. About that. Okay. Today's topic is 3 if we have the time, but 2 is very important. 1, 2, 3 is the option if you have time. Today's topic is namely new era in organic synthesis, and one is the palladium tetride coupling reaction. Palladium tetride coupling reaction. That is the Nobel Prize chemistry. 3 persons are winning the Nobel Prize in chemistry in 2010. And another one is the metathesis method in organic synthesis. This is also Nobel Prize chemistry. This is the option, but this is also the chirally catalyzed reaction I prepared. If we have time, this one might be presented. This is also Nobel Prize Chemistry 2001. So maybe the recent topics, all of the topics of the Nobel Prize Chemistry is covered in my talk. This is a little bit bad for the very, very early level of the undergraduate students. But please be patient about that. This is the prologue, typical conventional reaction. Maybe you understand very much. Example 1 is a nucleophilic substitution reaction. This is a very basic cis bond forming reaction, SN2 type reaction. Okay, carbonyl, chloride, highly polarized cis bond forming reaction is occurred by the anionic reaction. Okay, very well. Okay, so this is a typical case of the reaction. Can you understand? Sorry about that. Next is also nucleophilic addition. Carbonyl, carbonyl group, double bond. Also, this is highly polarized because this oxygen is highly electronegative atoms. So the polarized, in this case, ionic and anionic, polarized. So the carbonyl is attacked here to give the cis bond forming reaction. In this case, chloride is not green, oxygen is not green, CO double bond is a single bond, of course. Okay, so in this case, for example, green reasons is typical reaction, of course. Okay, so this type of the cis bond forming reaction is still the major tool for the cis bond forming reaction. This is surely the basic tool for the organic synthesis. But recently, completely different type of the CC bond forming reaction is widely used. So this is this palladium catalyzed cross-coupling reaction. This palladium catalyzed cross-coupling reaction is a Nobel Prize in Chemistry 2010. Okay, the Nobel Prize winner is Richard F. Heck, University of Delaware, USA, and Akira Suzuki, Hokkaido University. This is the north part of Japan, Japanese professors, and H. Negishi. H. Negishi is the American University professor, Purdue University, but originally Japanese person. This is the Heck reaction, very typical case of Heck reaction. Heck reaction is a very important for the fundamental reaction, all catalytic reaction. So the Heck reaction has many essence of the catalytic reaction. So this is very important. This reaction is not originally Heck reaction. This is some sophisticated, so improved method of the Heck reaction. In 1985, in this case, vinyl iodide, both vinyl bromide can be used. When this catalytic, this reaction, this iodide, vinyl iodide was allowed to react with many olefins. In this case, these types of the olefin can be used. In the presence of palladium acetate catalyst, the K2CO3, and this is a so sophisticated method. DMF is the solvent. This is the surfactant that is used for the high solubility. And in this case, the reaction product is the CC bond forming product in 91% yield. So this is a new type of CC bond formation, which never realized by the conventional anionic reactions. Okay, so I want to say about Heck reaction. Before precise things, I want to emphasize about the lost history of the Heck reaction. Heck reaction itself was found by Mizoroki, Japan. Professor Mizoroki is the associate professor of the Tokyo Institute of Technology, Tokyo. First, Mizoroki reported these types of the reaction. Okay, this reaction is almost the same as the Heck reaction. 1971. Britain Chemical Society of Japan, very small and unfamous, non-famous journal. This reaction is the phenyl iodide here, and styrene here, palladium chloride 0.1 equivalent here, and potassium acetate as the base, and methanol is the solvent, 120 degree, and yield of the CC coupling product is 90%. This is the first reaction by the Mizoroki. After 1 year later, Professor Heck reports this kind of the reaction. Okay, say, little bit change. 0.1 is decreasing to 0.01. And this is very nice. Base is a little bit changing, but this is base and this is base. Okay, methanol removing, no solvent. It's okay or not? Some person, it's okay. Some person, this is not so okay. So it's okay. And 120 degree is changed to 100 degree. It's okay. Yield, decreasing. Okay, so this is Heck achieved publication in 1972. Okay, please show details. This is Heck report. of this 1972. Palladium catalyzed vinylic hydrogen substitution reaction with aryl benzyl and styryl halide. Heck, Delaware, 1972. Okay, so this is a publication of Nobel Prize. Okay, he said, Mizorogi, first sentence is Mizorogi. This is nice. Mizorogi and co-workers have recently reported the palladium catalyzed reaction of organic compounds with aryl iodide and potassium acetate, as I told you, in methanol at 120 degrees. We have independently discovered this reaction. Okay, yes, and find that it can be carried out under much more convenient laboratory condition. Okay, that's okay. Than were used by Mizorogi, and that the reaction provides extremely convenient method for preparing a variety of organic compounds. So, okay, I don't say anything anymore, but okay, sorry about that. It's okay. And Mizorogi died in 1980. Oh, that is not happy. Mizorogi died in 1980 at the age of 47. So this reaction is Heck reaction. Heck reaction, Heck reaction, Heck reaction. Every person says the Heck reaction. Okay? And Heck is receiving a Nobel Prize. That is a very, very good thing, because Heck itself is reported very, very frequently and showing the importance of this catalytic reaction very frequently. That is Heck's achievement. And also, Heck is a very, very nice person, because this is, I think, a very nice sentence. Very nice sentence. I cannot do such things. Do you understand? You might guess I thought. Explanation, I think that so such kind of the logics. I am so nice person. But Heck, Professor Heck is a very nice. I think so. I think so. Anyway, this reaction is Heck reaction, not Mizorogi reaction. Right now, many persons say this is a Mizorogi Heck reaction. Okay, this is a very right expression, I believe. Okay, so I want to dig into the Heck reaction. But before this, this is the basic knowledge to understand Heck reaction. Heck reaction, to understand Heck reaction, very important point is three. One is oxidative addition. This is in organic chemistry. Oxidative addition is very important. Okay, this is the Vasca complex. Vasca complex is made by Vasca, Professor Vasca. And this is the iridium complex. Iridium 1, monovalent complex. And it's 4. CO and chloride. Chloride is an anionic ligand, and another ligand is a neutral ligand. Triphenylphosphine is coordinated in a transport. That's all. This compound is very reactive. And when this compound was allowed to react with methyl iodide, this types of the complex is formed. In this case, iridium 1 is changed to iridium 3, trivalent. And iridium carbon bond is formed. Also, iridium iodide bond is formed. In this case, this is a schematic representation of this reaction. Metal N plus is the N valence. and this CI-AB bond. Of course, this is formally two electrons sharing one bond. Two electrons of the metal is released here to give the next another bond. So this two bond is forming. This is oxidatively adds the metal. So this is what we call oxidative addition. This is very important. Another important reaction is reductive elimination. Reductive elimination is a back reaction, reverse reaction of the oxidative addition. In this reaction, in this reaction, palladium-2, dimethylpalladium, cis-dimethylpalladium, triphenylphosphine complex. In this case, this C palladium bond is created to give the ethylene and the palladium 0 and 2-triphenylphosphine is released. This is the back reaction of the oxidative reaction, and the two electrons return to metal. That is a reductive elimination. Another very important reaction is insertion reaction. Insertion reaction is two types. One is insertion into olefins. So, for example, metal, methyl is okay, ethyl is okay. Alkyl metal species is reacted with olefin. In this case, this type of bonding is formed. Double bond is changed to the single bond, and the C metal and the C, in this case, alkyl is okay, nitrogen C bond is okay. This type of the two bonding formation is occurring. This is formally, this olefin is formally inserted into this metal R bond. So this is an insertion reaction. Another insertion reaction is a CO insertion. Insertion into CO is a metal ligand to CO. The first reaction is this type of coordination of the carbon monoxide. And the carbon monoxide coordination, after that, this ligand is transferred to this CO. This CO is not inserted. This alkyl is transferred. This is a migration mechanism. Okay, so in this case, this R is migrated to give the acyl complex. This is insertion into CO. These three reactions is very important for the many types of catalytic reaction. Okay, so this one is some typical example of the Professor Akio Yamamoto, Japan, Tokyo Institute of Technology. This is a very nice example for the understanding how this types of step is important. In this case, the cis complex, diethyl cis complex, palladium complex. When this compound is allowed to react with CO, this is a CO bubbling. When the CO is bubbled, first reaction is, of course, the coordination of CO by the ligand exchange reaction. Thank you very much. Very kind introduction, and also I have had very, very fruitful time. Many persons are very, very kind, and also the scientific level is very high. So today's talk is the third lecture. So the third lecture is, I think, this one is for the, I prepared this undergraduate students, graduate students. But this audience is professional, so this is a little bit I'm afraid about that because this lecture is very basic lecture. But it's okay, so I can do that. Okay. So today's lecture is new methods for organic synthesis using organometallic compound. I know many professors is expert in this area. So please be patient. Really long time. Please be patient about that. Okay. Today's topics is 3 if we have the time, but 2 is very important. 1, 2, 3 is the option if you have time. Today's topics is namely new era in organic synthesis, and one is the palladium catalyzed coupling reaction. Palladium catalyzed coupling reaction. That is a Nobel Prize chemistry. 3 persons are winning the Nobel Prize in chemistry in 2010. And another one is metathesis method in organic synthesis. This is also Nobel Prize chemistry. This is the option, but this is also the chirally catalyzed reaction I prepared. If we have time, this one might be presented. This is also Nobel Prize chemistry 2001. So maybe the recent topics, all of the topics of the Nobel Prize chemistry is covered in my talk. This is a little bit bad for the very, very early level of the undergraduate students. But please be patient about that. This is the prologue, typical conventional reaction. Maybe you understand very much. Example 1 is a nucleophilic substitution reaction. This is a very basic cis bond forming reaction, SN2 type reaction. Okay, carbonyl, chloride, highly polarized cis bond forming reaction is occurred by the anionic reaction. Okay, very well. Okay, so this is the typical case of the reaction. Can you understand? Sorry about that. Next is also nucleophilic addition. Carbonyl, carbonyl group, double bond. Also, this is highly polarized because this oxygen is highly electronegative atoms. So the polarized, in this case, ionic and anionic, polarized. So the carbonyl is attacked here to give the cis bond forming reaction. In this case, chloride is not green, oxygen is not green, CO double bond is a single bond, of course. Okay, so in this case, for example, green reasons is typical reaction, of course. Okay, so this type of the cis bond forming reaction is still the major tool for the cis bond forming reaction. This is surely the basic tool for the organic synthesis. But recently, completely different type of the cis bond forming reaction is widely used. So this is palladium catalyzed cross-coupling reaction. This palladium catalyzed cross-coupling reaction is a Nobel Prize in chemistry 2010. Okay, the Nobel Prize winner is Richard F. Peck, University of Delaware, USA, and Akira Suzuki, Hokkaido University. This is the north part of Japan, Japanese professors, and H. Negishi, H. Takeshi is an American university professor, Purdue University, but originally Japanese person. This is the Heck reaction, very typical case of Heck reaction. Heck reaction is a very important for the fundamental reaction, all catalytic reaction. So the Heck reaction has many essence of the catalytic reaction. So this is very important. This reaction is not originally Heck reaction. This is some sophisticated, so improved method of the Heck reaction. In 1985, in this case, phenyl iodide, of course, phenyl bromide can be used. When this catalytic, this reaction, this iodide, phenyl iodide, was allowed to react with many olefins. In this case, these types of the olefin can be used in the presence of palladium acetate catalyst, the K2CO3. And this is a so sophisticated method. DMF is the solvent. This is the surfactant that is used for the high solubility. And in this case, the reaction product is the CC bond forming product in 91% yield. So this is a new type of the CC bond formation, which never realized by the conventional anionic reactions. Okay, so I want to say about Heck reaction. Before precise things, I want to emphasize about the lost history of the Heck reaction. Heck reaction itself was found by Mizoroki, Japan. Professor Mizoroki is an associate professor of the Tokyo Institute of Technology, Tokyo. And first, Mizoroki reported these types of the reaction. Okay, this reaction is almost the same as the Heck reaction. 1971, Bulletin Chemical Society of Japan, very small and unfamous, non-famous journal. This reaction is the phenyl iodide here, and styrene here, palladium chloride 0.1 equivalent here, and potassium acetate as a base, and methanol is a solvent, 120 degree, and yield of the CC coupling product is 90%. This is the first reaction by the Mizoroki. After 1 year later, Professor Heck reports this kind of the reaction. Okay, say, little bit change. 0.1 is decreasing to 0.01. And this is very nice. Base is little bit changing, but this is base and this is base. Okay, methanol removing, no solvent. It's okay or not? Some person, it's okay. Some person, this is not so okay. So it's okay. And 120 degree is changed to 100 degree. It's okay. Yield, decreasing. Okay, so this is Heck the achievement publication in 1972. Okay, please show details. This is the Heck report of this 1972. Palladium catalyzed vinylic hydrogen substitution reaction with aryl benzyl and styryl halide. Heck, Delaware, 1972. Okay, so this is a publication of Nobel Prize. Okay, he said, Mizoroki, first sentence is Mizoroki. This is nice. Mizoroki and co-workers have recently reported the palladium catalyzed aeration reaction of olefin compound with aryl iodide and potassium acetate. Yes, I told you. methanol at 120 degrees, we have independently discovered this reaction. Okay, yes, and find that it can be carried out under much more convenient laboratory condition. Okay, that's okay. Than were used by mythology, and that's the reaction provides extremely convenient method for preparing a variety of organic compounds. So, okay, I don't say anything anymore, but okay, sorry about that. It's okay. And Mizoroki died in 1980. Oh, that is a happy thing. Mizoroki died in 1980 at the age of 47. So, this reaction is Heck reaction. Heck reaction, Heck reaction, Heck reaction. Every person says the Heck reaction. Okay? And Heck is receiving a Nobel Prize. That is a very, very good thing, because Heck itself is reported very, very frequently and showing the importance of this catalytic reaction very frequently. That is the Heck's achievement. And also, the Heck is a very, very nice person, because this is, I think, the very nice sentence. Very nice sentence. I cannot do such things. Do you understand? You might guess I thought. Explanation. I think that so such kind of the logics. I am so nice person. That Heck, Professor Heck is very nice. I think so. I think so. Anyway, this reaction is Heck reaction, not Mizoroki reaction. Right now, the many persons say this is a Mizoroki Heck reaction. Okay, this is a very right expression, I believe. Okay, so I want to dig into the Heck reaction. But before this, this is the basic knowledge to understand Heck reaction. Heck reaction, to understand Heck reaction, very important point is three. One is oxidative addition. This is in organic chemistry. Oxidative addition is very important. Okay, this is the vascular complex. Vascular complex is made by Professor Vasca. And this is the iridium complex. Iridium 1, monovalent complex. And it's 4. CO and chloride. Chloride is an anionic ligand, and another ligand is a neutral ligand. Triphenylphosphine is coordinated in a transport. That's all. This compound is very reactive. And when this compound was allowed to react with methyl iodide, these types of the complexes formed. In this case, iridium 1 is changed to iridium 3, trivalent, and iridium carbon bond is formed. Also, iridium iodide bond is formed. In this case, this is a schematic representation of this reaction. Metal N plus is the N valence. And this CI-AB bond. Of course, this is formally 2 electrons sharing 1 bond. 2 electrons of the metal is released here to give the next another bond. So this 2 bond is forming. This is oxidatively adds the metal. So this is what we call oxidative addition. This is very important. Another important reaction is
reductive elimination. Reductive elimination is a back reaction, reverse reaction of the oxidative addition. In this reaction, in this reaction, palladium-2, dimethylpalladium, cis-dimethylpalladium, triphenylphosphine complex. In this case, this C palladium bond is created to give the ethylene and the palladium 0 and 2-triphenylphosphine is released. This is the back reaction of the oxidative reaction, and the 2 electrons return to metal. That is a reductive elimination. Another very important reaction, insertion reaction. Insertion reaction is 2 types. One is insertion into olefins. So, for example, metal, methyl is okay, ethyl is okay. Alkyl metal species is reacted with olefin. In this case, this type of bonding is formed. Double bond is changed to the single bond, and the C metal and the C, in this case, alkyl is okay, nitrogen C bond is okay. This type of the 2 bonding formation is occurring. This is formally, this olefin is formally inserted into this metal R bond. So this is the insertion reaction. Another insertion reaction is the CO insertion. Insertion into CO is a metal ligand to CO. The first reaction is this type of coordination of the carbon monoxide and the carbon monoxide coordination. After that, this ligand is transferred to this CO. This CO is not inserted. This alkyl is transferred. This is the migration mechanism. Okay, so in this case, this R is migrated to get the acyl complex. This is the insertion into CO. These 3 reactions is very important for the many types of the catalytic reaction. Okay, so this one is some typical example of the Professor Akio Yamamoto, Japan, Tokyo Institute of Technology. This is a very nice example for the understanding how this types of step is important. In this case, the cis complex, diethyl cis complex, palladium complex. When this compound is allowed to react with CO, this is a CO bubbling. When the CO is bubbled, first reaction is, of course, the coordination of CO by the ligand exchange reaction. This is the lithium and magnesium. Murahashi Sensei is my boss at my younger days. Okay. Professor Murahashi is a very big professor. He is a boss of the Chemical Society of Japan. Next boss of the Chemical Society of Japan, Noyori. So the Professor Murahashi is a very big boss. I was hard to find. Every time, very hard. Okay, right now. right again, right time. Doing the job. Okay. Anyway, this is Murahashi work. Very, very original work. Right? Very original work. Professor Suzuki used the boron. This is now very famous. Murahashi reaction is disappear. Every person will know you. Disappear. any person knows Suzuki, oh, very bad for me. Of course, this is very original, maybe you understand. Magnesium is the linear region, Brazil is a very, very fundamental metallics. This is the original one. But of course, Suzuki is doing the research simultaneously. So this is not a copy of ours. But boron chemistry is very nice because of course, very easy to be prepared. Maybe you know that this is very difficult. Okay? Very difficult. I did not sleep to prepare this one. Okay? Prepare this one. Professor Muraha said, okay. Very, very difficult, but I did it. This required 140 degree DMF solvent or something like that. One day reflux. Okay. Anyway, so this is a very nice reaction, but preparation is very difficult. Suzuki case, this one, okay, only telephone right now. In Japan, telephone to some company, and after 2 hours later, this one is returned. Okay. After 2 hours by telephone. That means this is very easy to be prepared and stored. This can be stored at room temperature, maybe under air conditions. Very nice. So the many person use this one widely. So the Murahashi reaction, nothing, nobody. Suzuki reaction, any person. So right now, only the Suzuki reaction is arriving. Murahashi reaction, and Naota reaction is nothing. Okay. And the Takeshi reaction, that is also very nice. Takeshi is a zinc. He used a zinc. Okay. Takeshi is okay. This is Malaysia. Okay, so very far place to Japan and USA. Takeshi is a copy of Murahashi. Okay. And Takeshi frequently did so this is our lab talking with Murahashi. Very nice, very, very nice person. Okay. But this and zinc is very nice, very, very nice. This is a Reformatovsky region. Very similar to the Grenier region. It's very easy to prepare. Zinc zero. Zinc zero is a sort of black, gray powder. Very easy to be prepared from the bromine. Many compounds can be prepared. And nice things is, for example, CO2R is okay. In this case, CO2R here, very bad. Very bad. Intermolecular reaction. Carbon is attacked. So this is impossible. But in this case, CO2R attaching CO2R carbon group is okay. So this is a very nice application. Okay. Sonogassila coupling reaction is also very nice reaction. Like this. Nowadays, this types of the reaction is fundamental for many types of the supramolecular chemistry because of this high conjugated product is very, very precise right now. So the many persons use the sonogassila coupling reaction. Okay. And after that, okay, this too is awarded. Of course, okay, the original one is the preparation is difficult. Nobody, only the affording the original idea. That's all. Okay, very specific. Okay, so that's bad. Okay, Suzuki, very easy and versatile. Many applications can be obtained. Zinc is the same. Very easy. This kind of the compound is easily prepared, and of course this compound is stable, easy, versatile. Okay, how about copper? Copper is very easy and very precious for some special purpose, very nice, but specific. Okay, so this and this is Nobel Prize. Okay, that. This is real history. Real history. If you think that I tell a lie, please visit the Nobel Prize website and read the reason of the Nobel Prize precisely. Okay, this is right. But that Nobel Prize explanation ignored Mizoki. Okay, ignore Mizoki. Brash does not ignore. Okay, so yes, this technology. And this one is a Suzuki Miyaura coupling reaction. This is right now very nice compound method. For example, this type of the complexes is iridium complexes. This iridium complex is very useful for the OLED. Okay. This iridium PBY is green. And if the F is attached, this is blue shifted very much. And if this aromatic moiety is changed to the non-pure moieties, in this case, this is extraordinary reddish. So the red RGB can be easily repaired. And of course, this compound is maybe in your pocket right now in your pocket. Maybe this is not so good. This types of the complex is in your pocket, in your iPhone, surface of the iPhone. So these types of the complex can be easily prepared by these types of the Suzuki coupling reaction. And after the iridium chloride putting to give the relative dimer and many ligands can be obtained after that. So now I prepared these types of complexes, but I cannot say use the Murahashi method. I cannot say because this is so easy, very easy. Okay. Of course, my method, these types of the compound can be prepared, but I cannot say. So the time is changing. Okay, so this is the next type of object. Next is the metathesis method. Metathesis method in organic synthesis is also the Nobel Prize chemistry. 3 persons win the Nobel Prize for the development of the metathesis method. This is Robert Grubbs. Robert Grubbs is the California Institute of Technology. Very tall person, 2 meters, very tall person. Richard Schrock, MIT, Massachusetts Institute of Technology. And Chauvin, France. Okay. The olefin metathesis is a very historical thing. This is a discovery. Some past Calderon, Professor Calderon reported very strange type of the reaction in tetrahedron letter. His case, this kind of the tangle state catalyzed, that is a mixture of the diethyl aluminum chloride. This is the so-called Ziegler nut catalyst, the very same types of this type of catalyst, olefin polymerization catalyst. When these compounds are allowed to react with this mixture of catalysts, 2-pentane, from 2-pentane, 3-hexane and 2-butane is obtained. Oh, this is Y. Red and blue is red and blue. Okay, so this is some kind of discrimination is occurring. This is some kind of enigma. After 3 years later, some person, Chauvin, suggests this mechanism. The first thing. He only thinking about that. This one is a carbon complex is for maybe, and carbon complex is reacted with the olefin, that olefin, ethyl and methyl. React with the 4-membered metal cycle, maybe, he said. Okay, so when this 4-membered metal cycle is formed, this one is free. If this direction, cleavage is this going this direction, the original compound. But when the cleavage is occurring in this direction, this is different types of the carbon complexes formed, and this already formed. After that same series, when this carbon complexes react with the same olefin, 4-membered metal cycle, and if the cleavage is occurring in this direction, in this case, R1 olefin is now formed with the liberation of the same types of the carbon complexes. And this carbon complex is reacted with this olefin to give the 4-membered ring, and when this direction cleavage is occurring, in this case, okay, so R2 olefin is formed. So this is some solution for this enigma, suggested mechanism. So the Professor Chauvin received the Nobel Prize only that. This is a very, so the efficiency is high. Nobel Prize efficiency is the highest. Only thinking that. Okay, so, but the Grubbs, after the 20 years later, Grubbs reported a very, very nice application. That is the ring closing metathesis. Okay, Grubbs used this ruthenium carbene complexes. As this one is will be described later. This ruthenium carbene complex reacts with this terminal olefin compound to give the ring closing compound with the liberation of the olefin. The mechanism is very, very understandable. When this compound is allowed to react with the ruthenium carbene complexes, this 4-membered ring is formed first. And this 4-membered ring creates this. In this case, the olefin is liberated, and another big carbene complex is formed. And this carbene complexes react in a intramolecular manner to give another 4-membered ring compound. And this 4-membered ring is created the same olefins to give the catalytic species, regenerating the catalytic species, and ring closing product is formed. So this is the mechanism. Grubbs catalysts, there are many types of the Grubbs catalysts right now. The first generation Grubbs catalyst is like this one. dichlorotrifosphine. This is a very stable compound. This one reacts with this type of the highly reactive species to give this carbene complexes. Almost 100% yields. Another is like this one. This type of complex is very, very stable and very easy to be handled. For example, if this one is subjected to the hydrogen chloride, react with hydrogen chloride, this one is not react. So the very, very stable and easy to be handled and also stored. So nowadays, this complex is obtained commercially. This is a typical case of the ring closing metathesis reaction. This is very nice organic reaction. For example, this alkane is a very nice thing. This is simple diarylamine, protected diarylamine, very simple compound. This simple compound reacts with this catalyst to give this compound. Okay, so this compound very difficult to be prepared by another method because this is very difficult. But in this strategy, 90% yield this compound can be obtained. Also, this type of very, very difficult compound because olefinic part here is very easy to be prepared. This part very, very difficult. This type of the complex is compound is very easily prepared. So this is perhaps catalyst is very nice. Amazing progress has been made in ring closing metathesis. That is a one-step synthesis of macrocyclic complexes. And this is made by the European professor Sina. He published this kind of the amazing organic transformation. Okay, this compound is alcohol, and this is the carboxylic acid, long alkyl chain, 2 pound is the olefin at the terminal part. So this compound is originally not this compound. Long chain. That's all. But this long chain compound does react with this Graham's catalyst. 71% yield. This 21 membered reactor is formed. This is amazing for ordinary organic chemistry because carbonic construction, if you are the organic chemist, you will understand that 6-membered ring is very, very easy. 5-membered ring is also easy. 4-membered ring construction, very, very, very difficult. Okay, so 7, 8, 9, 8, difficult because so polymerization is occurring in chemical reaction. How about the 21 atom? If that kind of the complex compound is formed by the usual method, the originally starting material should be this one, this. Okay, so 20 atoms, very difficult to meet together. This is very difficult. So probability of the meeting is very, very low. So in this case, selective polymerization is occurring. So this kind of the strategy, many persons is surprising very much. I am also very, very surprised to see the first in 1997, 1996. Very surprised. So the Professor Nicola with some kind of superstar of organic synthesis. He is a professor from California. Okay, so he prepared this epoxy A, after reading the paper for 1 year, he prepared epoxy A, only 1 year. Okay, so this compound, by using this organ, and this organ is reacting with the same catalyst to give 60-member ring. Okay, this is very difficult thing. And after the epoxidation, after the removal of this protective group and epoxidation, this is the final product. Epoxy of A. This is a very strong anti-cancer drug. So he prepared. 1996 is this publication here, and 1997 he published this one. Very fast. Okay, so this is not second step reaction. Okay, maybe the 30 step, 40 step reaction. Both 40 step reaction is the trial and error. But he made this type of the synthesis of this type of products. Only 1 year. Amazing. Another application is, of course, many types of application. This application is a very famous professor, Shiki. Samuel Shiki is the professor of air. Forget. In this case, he prepared microstatin. Also, this is a very strong anti-cancer drug. In 2005, 67% from this oil. Very similar things. Okay, another application of Graves catalyst. And it's okay. Graves catalyst is like this one. Okay, this is the high yield synthesis of catenan. Catenan is a ring type compound. Okay, so how to say, interlocked rings without bonding interaction. Maybe you understand soon. But in English, how to say? It's okay, interlocked rings without bonding interaction with catenan. Okay, so this catenan can be obtained by using this method. Maybe you understand. But okay, so conventional method of synthesis of 2 catenans here. Catenan itself is the first published in 1960 by Wasserman. Wasserman by using the acyloid condensation of this compound. Using this long alkyl chain ring compound with the long alkyl diester is reacted in the presence of sodium and acetic acid. This is a normal acyloid condensation condition. And okay, so what is the reaction? Of course, the reaction is a simple reaction is the polymer reaction, and another reaction is the ring type reaction, and very small amount is passing through here and making a ring. So this compound is from 0.0001% yield. Wasserman report this one using the pasta. Real pasta. Yes. Pasta. Okay, pasta. Okay, this is the real thing. So, this is a very dangerous thing. Yeah, this smell is very bad. Okay, pasta, real thing. Okay, so this is how this is difficult. So, Graves catalyst strategy is here. The first thing is the preparation of this compound. Okay. First, Rotaxane should be obtained. Okay. This ring, first taking this ring compound. Okay. So this is the nitrogen here,
And this type of compound, the chain compound, nitrogen here. This is a schematic representation in place. In this case, schematic representation is this. And this compound react in the presence of the stoichiometric amount of the kappa 1. Okay? So the kappa 1 is coordination here. Because kappa coordination is a heterohedral coordination. So this kappa is like this one. So in this case, the reaction is like this one. Rod through ring. This is what we call rotexane. So the rotexane is in this case 100% yield. This is very nice. After that, maybe you understand. Yes, right. The ruthenium catalyst gives this 32 method ring in 92% yield. Wow, very nice. Because this one is the congested. Constrained right now. Constrained is formed. So this one is not so good. So this is very easy to plot here. So 92% yield. After that, this copper is removed by KCN. Because CuCN is very nicely and very good for the this is stable. So every copper is changed to CuCN. So the copper is nothing. Okay, this yield is 100% yield. So total yield is 92%. This line, because nitrogen. But this is a very amazing thing. Right now, this kind of things can be obtained. Okay, so the time is closing. So my lecture is ending. Fine? Yeah, it's okay. It's okay. It's a little bit time. It's wrong. So thank you very much. Thank you.
Thank you, Professor Takeshi Naota, for the good information, introduction in the organometallic chemistry based on the Nobel Prize finding. So we would like to open the session for the Q&A. Any question? Please, from the student. You can ask how I can do. Yeah, please.
This compound that you just discussed about is really, really interesting. I'm just wondering how they confirm that they prepare this type of compounds, the interlock compounds, because there's no bonding between the two rings, right? Yeah. You get the question? I'm wondering how they confirm they have prepared this type, of material.
This is not my result, so I cannot say exactly, but in this compound, yes, the first thing is maybe the mass spectrum. Of course, another evidence is NMR spectrum. In the NMR spectrum, maybe some difference is occurring by the ring current effect. So the shielding effect is changing by this approaching to basically
Any more questions? I have one question.
Okay.
Based on this lecture, New Era in Organic Synthesis, what do you think for the next generation of the organometallic, especially for the
Next generation, I don't know that.
after 2010? So almost every 5 years there is Nobel Prize in this field.
I think nowadays, any age is an ionic reaction, anionic reaction, and also the radical reaction. This kind of the reaction from age. And after the head reaction, the metal catalyst is nowadays making trends for the development of the new reaction. So the metal nowadays metal catalyst is changed to the CX bond-privilege to the CH bond-privilege. This is we call the CH activation. CH activation is very good because there is no halogen. Halogen is very bad for many reasons. But CH activation is no halogen. So this is a very sort of environmentally benign process of highly sustainability or something like that. That is our major influence. Metal catalyst. Nowadays, metal catalyst is changing gradually to the development of the organic catalyst. Organic catalyst is, for example, triethylamine. That is organic catalyst. But nowadays, much more so complicated organic molecule can do it a very nice reaction. Okay, so another is synthetic enzyme or something like that. In this case, metal catalyst, organic catalyst, so the purpose and goal is high selectivity, and also versatility is very important. For example, methyl okay, ethyl okay, phenyl is okay, and alkoxy group is okay, and isopropyl group is okay. That is very in that high versatility is obtained in the reaction. Many persons can be used. So this is our every time our purpose, goal for the creation of catalytic reaction. But some person right now say specificity. Specificity means one compound reacts, only one compound, and another compound not react. Bromide, carbon compound, but for example, phenyl and methyl groups here, only that compound is react. And methyl is ethyl, no reaction. That is the specificity. That kind of specificity is right now many persons is interested in. Okay. Also, sustainability is very important for our daily life.
Thank you for the answer. I still would like to open for Q&A anymore. If there is no more question, I would like to invite Professor Masin Sanadi to give appreciation to Professor Takeshi Naota. Please, thank you, Professor Takeshi Naota and Professor Marcin. After this, we have